Hey, what's up? So it is Monday. It is 8:45 p.m. Just finished taking a shower. Worked out a bit today, and I thought I'd start filming now because, well, why not? So I have a couple of things to do before I go to bed tonight, and then wake up the next day and do more stuff. So I was thinking. The next part in my lecture has to do with neutron stars, pulsars, and black holes, which is, well, fancy stuff. And it's lecture 11. As you remember, we finished up to lecture 10 in the last video. So I'm going to go in a little bit of depth into this as and when I touch on certain topics. And after this, I'm going to start with a chapter in my classical mechanics book. I've never done stuff from this book before. It's a new exposure for me as well. So I'm going to refer a video myself. I'll see which video I'm referring to. I'll leave the link in the description. You guys can check it out too if you guys need help with that. So I'm going to start off with Lagrangian dynamics, and you can actually check this book out. It's Classical Mechanics by J.C. Upadhyay. It's a pretty good book. It's a really good book. It's more of a reference book than a guide, if you will, and it's got solved problems and examples. What more do you guys need? It's really good. So I'm going to get down to doing this. We'll start off with this first, then we'll get on to that. So let's go. Alright, so I have reached a point in the presentation. We've touched on neutron stars, we've touched on pulsars, and now we're on to black holes. So it's quite interesting when you think about it, because black hole is a term that's just thrown around quite a lot by a lot of commoners and people who are just interested in physics, but there's so much more to it than just what's on the surface. So basically, there are stages of stellar degradation, if you will, based on the masses of the stars, right? So there's something called the Chandrasekhar limit, which is approximately 1.4 times the mass of our sun. So any star below that limit is gonna form a white dwarf or something of the sort, and anything above that would form a neutron star. So the principle of supporting these stars is quite simple, actually. So in a white dwarf, you have the electron degenerate pressure. Now, what that pressure is, in a sense, is when you have, in a confined space, if you have a certain amount of particles, each of them will acquire a certain quantum state, and after all the states have been met, they start to exert a pressure. So that balances out the pressure that the gravity is exerting to collapse the star. So in white dwarfs, it's electron degenerate pressure, and in neutron stars, it's neutron degenerate pressure. So that's what keeps these stars stable. That's what keeps them compact, right? After they go supernova, that's how they stay in that particular shape, right? But black holes is different. So anything above 3 solar masses, you can't stop the collapse, right? It overcomes electron and neutron degenerate pressure, and it's just gonna sink through to form a black hole. So that's basically what they're talking about here. So if you see here now, I've read supermassive black holes in the galactic nuclei. So what this is talking about is that in every galaxy, there's been a study conducted that there is a black hole or a supermassive black hole at the center of these galaxies, right? So black holes can form of various shapes, sizes, and radiuses, basically. So if you see here in the PPT, you can see there's a particular slide that talks about this very thing, which is here, the structure of black holes. So you have a singularity, you have an event horizon, and well, if it's part of a binary system, you have an accretion disk around it, but that's secondary. So black holes can be of two types. One of them will be really small, they don't have any rotation to them, so those you can measure the radius of those. That's known as the Schwarzschild radius, which is given by r is equal to 2 gm by c square. And if the black hole is a rotating black hole, things get a little more complicated with space-time, general relativity coming into the picture and all that sort of. So it gets a little shitty from there. But this is just the basic structure of it. So what the singularity is essentially is that when the star undergoes a core collapse, when it just collapses, the radius of the core is essentially 0, right? So that's what the singularity is, and the event horizon is the zone around it where the escape velocity beats the speed of light. So escape velocity is basically how fast you need to go to escape the gravitational pull of any object. For example, of Earth, it's 11.2 kilometers per second. So it varies with different planets and different cosmic structures. But for black holes, it's faster than the speed of light. So that's why black holes, you can't really see through them. And that's just the gist of what they are explaining about. And they go on to talk about gamma ray bursts and all of that, and confirmation of the general theory of relativity, which is a very beautiful thing. So when Einstein discovered, or rather had the intuition that mass bends space-time, and we will talk about general relativity in one of the videos if you want to, but when he discovered that mass bends space-time, like, how do I prove this? And then he's like, wait a minute, if star is there and the light is coming, it'll bend. So then he's like, Eddington, I want you to go and I want you to measure this for me. And he's like, oh, he's like, just go and measure it. So then he went and they conducted the whole experiment, and they were able to detect a deviation in the angle there. So that's what they're saying, it's 1.78 arc seconds is the angle. If you see the real place where the star is and the observed place, that this deviation in the angle of the apparent and real position of the star, absolutely beautiful how they verified the general theory of relativity. But anyway, moving on from that, I've reached a significant part, I feel, in this presentation, and what I'm going to do now is I'm going to take the tests that are there. So basically, after going through the PowerPoint presentation, the first one, you have to attend a series of tests, and then after you're done with the final one, you'll get a new PPT, and that covers one session. So once you're done with the other set of tests, so I'm going to finish up with the tests. I'm going to take a little bit of a break, eat something probably, because it's 9:30 now, and then I will start off with classical mechanics as promised. So before starting off, I will give an introduction as to what I'm going to do, where I'm starting, how I'm going to start off with, because I'm thinking I'm just going to go through the book first, just get an idea of what the chapter is all about. If it goes over my head, then I'll probably watch a video about it, and then the book might make more sense to me. So I'm just going to attend the tests now, and I will see you after having done those tests.
And interact with the target. So what that means is that all of these processes.
So I finished eating, took a nice long break, thought I'll start now again. So not gonna lie, I did go through the book, and it does seem a little bit, the terms are a little new. So what I'm gonna do is I'm gonna quickly go through the video. Quickly, I'm gonna take my time. It's gonna be a cut or something for you, but I'm gonna go through the video, and I'm gonna see what I get out of that. I'm gonna make some notes. After that, I'm gonna try to read the book, see if anything makes sense to me. If it's already in Latin, then well. So I'll see you then. Hey, so it is officially the end of the next day. Completely skipped over a day there. But so to sum it up for you, I didn't actually do much today. What I did was, just woke up in the morning at around 9:30, freshened up, revised through what I did yesterday, went through the video. It was a really helpful video. The instructor was speaking in a mix of English and Hindi, so if you don't understand that, then well. So I'll leave the link in the description of the video that I used for reference. And the video as such does not give you a complete, in-depth analysis. It just touches and goes on many of the topics that are there in the chapter. And after having gone through the video, using the book did help a lot. So I'm just gonna call it a day now. It's past 1 even now. So I guess this is the end of the video. Stick around for more such content, and I'll see. Probably in the next video we can dive into depth into more of textbook stuff, or probably I'll make a video based on one specific topic, just a short video. And until next time, peace out.